We have established now that the binomial distribution has a unimodal character. The binomial probabilities increase up to an integer in the vicinity of n times p and decrease thereafter. Let us turn now to what is visible, what is clear in the figure, that there is a centering tendency, a center around which the binomial probabilities are roughly evenly distributed. Consider the setting where we have 10 trials, 10 tosses of a coin whose success probability is 0.6. The binomial probabilities are as shown in the figure. It is clear that there is a unimodal character, and the maximum value, the largest probability, occurs exactly at n times p, in this instance at 10 times 0.6 or 6. Now, to capture the idea of center, we turn to an idea common from physics, the notion of a center of mass. To put this in a proper context, it might help if we simply flip the figure. Imagine that at each of the values, 0 through 10, we've got a mass attached whose weight is given by the binomial probabilities. Now, if we have a setting like this, we have a distribution of masses. Imagine temporarily that all the masses were the same. Then we have a setting like this, approximately, where we have a uniform distribution of mass. Now, think of a seesaw. Where would the point of balance be? Where would the fulcrum be? That is the center of mass. And in a situation where the mass is evenly distributed, the center would manifestly be right in the center, in the middle. But if the mass were unevenly distributed, as is the case in your figure, then one has a setting perhaps like this, where mass is larger at one end than at the other. Now, in this case, we would not have equilibrium right in the middle, but in fact the center of mass, where both sides are balanced, shades towards the larger masses. Now, this is exactly the kind of setting we have in front of us. We now want a mathematical prescription which captures this idea of this probabilistic center of mass. Common convention refers to this by the Greek letter mu, and we write it down exactly as we would in physics, as follows. To the point 0, we attach a mass whose weight is b of 0. To the point 1, we attach a mass whose weight is b of 1. To the point 2, we attach a mass whose weight is b of 2. To the point k in general, we attach a mass of weight b of k, and so on. This weighted sum then gives us very naturally the probabilistic analogue of the physical idea of a center of mass. Now, it is comforting to write a long sum like this down because it makes transparent exactly what each element contributes. But when one does an analysis, it is convenient to compact this using summation notation and write it simply in the form as a summation over an index k, which varies in this case between 0 and n, of quantities of the type k times b of k. The connection with the physical center of mass should be transparent here. We call this the expectation of the accumulated successes S sub n, and we denote it by E of Sn. E, of course, stands for expectation. Sn is the accumulated number of successes in our chance experiment. And this is also referred to sometimes as the mean or the expected value. And of course, one recognizes in this just a generalization, the analogue of an arithmetic average. Now, all these terms are useful. They add color to the picture. But especially for a neophyte, someone starting out in the game, it would be advisable to think of this object by its formal mathematical connotation, by referring to it as a mathematical expectation, meaning therefore that there is an underlying very specific mathematical formulation which captures this. And in this case, of course, it is a weighted sum. In many cases in practice, when there is no ambiguity, by a long force of tradition, we will simply call this just mu. But when there are more than one chance experiments at play, then we will refer to it particularly as E of Sn, the expected value, the expectation of Sn. So now we've got a formulation. We've now got a mathematical model for a center of mass. Our next question then is, well, what does it evaluate to? Of course, we could compute this numerically. If you tell me n is 10 and p is equal to 0.6, we could just simply write down an arithmetic sum, evaluate the values, add them up, and here's an answer. But of course, this is not very satisfactory. It doesn't give us a feeling for the problem. It doesn't tell us how this expectation depends upon the number of trials n and how it depends upon the success probability p. So what we are looking for now, what we are casting about for, is a simple, compact, mathematical simplification of the sum, which makes transparent for us the roles played by the number of trials n and the success probability p.